here we have about a 3 millisecond capture of a pulse signal with, it kind of looks like a repeating pattern, but we're not 100% sure, with varying pulse widths and PRIs. And what we've done here is that in our measurement setup and pulse properties, we can now take a look at obviously our setup for pulse detection that we've talked about before. Things like our time tab. Here's our 3 millisecond capture, and this is over a bandwidth of, again, 160 megahertz. But since we're not interested in looking at the frequency content here, we're mainly going to stick with time domain views. But what we can do is we can look at the overall measurement of, say, 100 pulses, and we can see by changing this select subset, we can look at 100 pulses here, and that's, again, what's represented in the amplitude measurement time. But more so, we kind of see a little bit of a pattern here where we have several, where it looks about 1, 2, 3, 4, 5, 6, 7, 8 narrow pulses, and then some wide pulses before it starts repeating again. So it looks about 19. So I'm going to change the starting pulse to be 1, and then I only want to look at 19 pulses. So I'm guessing that this is one cycle of this waveform. So within that, we can see pretty easily within our pulse table, we have 130 pulses, and it's kind of difficult for us to determine if there's an overall pattern here. And we can certainly use our statistical analysis tools and histograms and trend lines, but another really interesting way to validate if there's a single pulse that occurs many times or multiple pulses that occur several times is to use the scoring functionality. So let's use that. So I'm going to go into the measurement setup and then pulse properties. And then within this pulse properties dialog, I'm going to select analysis. Now in the analysis menu, I have several options. We have our pulse modulation analysis to determine what we want to automatically demodulate. We have correlation, like we talked about, in terms of the overall measurements for time side lobe. And then we have scoring. And scoring is really interesting in the sense that we can select a pulse or provide a series of pulses that we want to use to score what we captured against. So to do this, we're going to simply select Scoring Enable. And you might have noticed after I checked that, you get this extra column here in the pulse table called Scoring. Right now, everything's a 1, but let's ignore that for just a moment. And let's select as a reference pulse pulse number 1. So we're going to start at number 1 and stop at number 1 for when we copy this over. So I'm going to say copy measure pulses. So this is going to take the exact information from pulse number 1 from our pulse table here, so minus 53.83 dBm for our top level, and it's going to copy this pulse width number, PRI, frequency, as well as the FM slope if there is any measured. And it looks like this one's a Barker pulse, so there's no FM slope. We can even select what metrics we want to score against. So let's turn on all of these here. And basically what we've done is now we're using this very first pulse to score against every other pulse in this whole table. So you could see pulse 1 compared to pulse 1, we have a high correlation factor. We have a 1 because everything we copied from this matches. And then subsequent pulses we see are low. They're exceptionally low, 0, 0, 0, 0, 0, 0, 0, 0, all the way till we get to pulse 20. So this is interesting because what we just talked about is we had a hunch that the first 19 pulses were the sequence in this overall waveform pattern. So that means pulse 1 would reoccur at the 20th captured pulse here in the waveform, which holds true here because we have a high correlation factor, 0.945. So if this is true for the whole waveform, we should see another close to 1 score for pulse 40. So let's scroll down to pulse 40. Let's look at that. It's at 39. That makes sense because I have a 19, 1 through 19, and then I start over at 20, so 20 plus 19 is 39. That makes sense. It's just mainly a counting error. But we see it's a little bit worse off. So maybe there's some amplitude variation or things like this. But you can see really quickly that we could pick out pulses that are close to being correlated, and we can easily identify those to drive into them deeper to really understand those characteristics better. Now, something even more important is, let's do this. Let's go back to pulse properties and back to analysis. And instead of using um, just one pulse, our first pulse, I'm going to delete everything in our reference, and I'm going to say, let's copy the first 19 pulses. So if this holds true, our first 19 pulses should all score 1 because they're compared to one another, and then the subsequent pulses should have a really high score factor. So here I'm going to copy those measured pulses, and we're taking in all that information. So now we have pulse 1 through 19 as our references, and we're scoring them based again on amplitude, width, PRI, and frequency. So if we go back to our pulse table here, we can see pulses 1 through 19 all score 1 because we're measuring our reference compared to our first 19. And then we can see that 20 through 39 are all high again. So this gives me a lot of confidence in understanding that these 19 pulses are functionally the same, just repeated over and over again. And maybe there are some minor capture issues from when I was recreating this signal in hardware that is leading to some lower pulse scores here. Maybe there's some frequency accuracy issues and so on. And just to test that, what we could do is let's go down here. Let's kind of take a look at 40 and beyond. So 40 to 59, we see we have kind of some 0.8s in there and so on. If we go to our scoring dialog, and let's turn off the frequency, all right, and let's turn off the amplitude, all right, we see those all went up. So the question becomes, you can easily, just by doing some check marks, very, quickly understand which is a larger source of contribution in terms of the error to some of these, but also you can adjust the base error for each of these figures. And the base error is basically a weighting factor for each metric into the overall equation for the pulse scoring algorithm. And if you want to see that equation in more detail, you can easily go into the help dialog, and by pulling that up, we should be able to view what that looks like. So we're going to go into scoring metric, and we see here that the error RMS, or the score, is the exponential of the negative error RMS. And error RMS is the square root of 1 over n, where n is the number of scoring metrics. So the scoring metrics is what we see here. So top level, width, PRI, frequency, mean, and slope. So n can be 1 to 5, and it's the summation of that over the course of x sub I minus r sub I divided by e sub I, and all that squared. X sub I is the measured value. So that's the measured value. So that's the value coming from the pulse table. So in this case, it would be, say, this particular pulse width value. R sub I is the reference value. That reference value is what we have in our reference table here, whether we copy those from something that was measured or we recall them from a user-defined file. And then E sub I is the base error. So this weighting factor is going to functionally adjust how effective or how large of an error you can tolerate, and how that's going to affect the overall score. So if you have a little bit of frequency error, do you want that to be highly impactful on the score? Or if you have a lot of frequency error, do you want that to be minimized in terms of the score? So all this is really a way to do a couple things. One, to quickly validate that one or a series of pulses matches up to itself as well as others from an idealistic definition to what you capture, but also you can identify trends of if a certain pulse appears over time within a recording or a capture.